Hello everyone, so in this video I'm going to give you some quick solutions to all the questions. We have 4 questions here in quiz 3. Okay, so the first one, question 1 is about how to calculate, determine the specific enthalpy. So that's H, right, lowercase h, for nitrogen. Okay, so as I covered in quiz 2 and also in the properties of property of the water and the steam. So when we use that steam table, okay, so we use steam table, you can see that we can find the internal energy, specific enthalpy. We can find all these properties of the water and the steam. However, for the nitrogen, because nitrogen, which can be regarded as an ideal gas, okay, so it's not water and the steam, so we can't use that steam table to find out the specific enthalpy. Okay, so we need to use another calculation. So this also being included in the formula sheet, okay, because this is ideal gas. As I said, it's all in this section, ideal gas equations. You will be able to find out one equation, the last line, H, so this is specific enthalpy, is equal to U plus PV, okay. U plus PV, this is a general definition of enthalpy, so it applies to everything. It applies to ideal gas, it also applies to the steam, everything, okay. However, for ideal gas, because we have that one here, you can see PV is equal to RT, okay, so that you can replace PV here with RT. So that H is equal to U plus RT as well. And this bit, only applies to ideal gas. Okay, and now we're going to just use that. H is equal to U plus RT for this question 1. So H is equal to U RT. Okay, so we just check the question. We know the temperature T, so T, okay, so obviously it's in centigrade, so you convert that to Kelvin. We know specific internal energy U, so we know U here, okay, T, U, and we just need to, determine R here, okay. And in this section, so how to find out R is R0 divided by M. So we need to calculate R first, by R0 divided by M. So this M is not a mass, so this is a molar mass of a gas, as you can see here. Okay, R0 is that, divided by 28. Okay, and this will give you the R number. Okay, so I can do that. Is 8.13. So this gives you us 297. Okay, 297. Be careful about the unit. So this is the kilojoule here per kilogram. Okay. So once we find out R, then we'll be able to calculate U. Calculate H. U is there. 2642 at R. Okay, so we can just double check the unit. Actually, for this module, we need to be careful, very careful about all units. So you can always check. For U, that's kilogram, kilojoule per kilogram. Okay, so as I said here, that's the unit for R. But when you times a temperature, which should be in K, okay, so that's the temperature needs to be 273 at that 17. So this will have a K and the K will be cancelled. So you have a kilojoule per kilogram left. So that's the same, okay. And by calculating that, you will be able to get 2728.11 kilojoule per kilogram. So that's all the same, kilojoule per kilogram, as also being required here in the unit of kilojoule per kilogram. So that's your final answer, right? H. That's for question 1. Question 2. So in question 2 it says a gas enters a nozzle. Okay, so once we see enters, and a nozzle is a device of an open system, so we immediately know that this is a question about an open system. And from the formula sheet, okay, anything about open system has been listed here. Okay, so we have first law of thermodynamics, but in this case this applies to open system. And we also have a mass flow, how to calculate the mass flow rate by using that. So basically we just only have two equations to describe any open system. So we just copy that. Okay, the first one looks like a bit long, but we can have a look at how can we simplify that. Okay, m dot h2 subtract h1. So I'm just copying that down. Because we definitely need that equation, because this is only one, as I said, describing the open system. So now this is a nozzle. Okay, so now have a look how can we simplify this equation, because it says neglecting the heat transfer. Heat transfer is 0, okay, and the change is in potential energy. So that's a kinetic energy, that's a potential energy. So we can neglect that as well. Okay, so this is not end. This is because for a nozzle, although it has not been stated here, but we should understand that for a nozzle, so nozzle is a device we use to change the velocity, to greatly change, increase the velocity. Okay, so actually in this module we only have two devices. One is the turbine, which can be used to output work, so that will be work transfer inside the turbine. Also have compressor, so we need to input the work so that the compressor will be working. So apart from these two devices, all these devices such as a nozzle will have no work transfer, because there's no moving parts in the nozzle. So that this is not being given in that question, but we need to understand that this is actually 0 as well. There's no work transfer in nozzle. So you can see 0, 0, which give us everything 0. Okay, so m dot is not in here, but we know that no matter m dot, what's the value of m dot, and then m dot times something have to be 0, and here has to be 0. Okay, so finally we can simplify as that. Okay, so that's the final simplified form. So here I'm just to demonstrate how to simplify the equation again, but you don't have to do that in your final exam, because this the simplified form for all the 5 devices. I think I have already summarized in a table in the revision lecture slides, so you can check. You can just find out that equation, list that immediately, so you don't have to do this simplification. So okay, so now I'm going to use that to calculate the H2 here. Okay, so now H2 is equal to, move everything to the right hand side, so H1 at C2 square, sorry, this should be sub minus, okay, because I'm moving H1 over here, get positive, this is positive, move over there, get negative, half C2 squared subtract C1 squared. If you have a look at the question, so negligible velocity at inlet, okay, and the inlet, so that's H1 being given, C1 actually is 0 because it enters with a negligible velocity, so C1 is again 0, so this makes even more simpler. So that's it. Okay, so also the final form is very simple, but you need to be very careful again about the unit. Okay, so the H1 here is 2, 5, 6, 7. Okay, careful, that's in kilojoule per kilogram. subtract C2 505 squared. Okay, one very common mistake here is that cubic, so velocity here, velocity is meter per second, so that's SI base unit. So that's SI base unit. However, this is not. This is a kilojoule. Okay, so this is one way that you can multiply by this one by 1000. Okay, so that you convert in kilojoule to joule. Okay, and then you get everything SI base unit, which will be joule per kilogram. However, the final answer is that you need to write the answer in the unit of kilojoule per kilogram as well, because I said this is a big number. If we convert to joule per kilogram, it will get even bigger. So you can do another way, is that you keep this. Okay, you keep this kilojoule per kilogram, so that's the same unit of your final answer. However, it divided that one by 1000. Okay, so this unit, this term will also be in kilojoules, in kilos. Okay, so that you make these both terms consistent with each other. So this, as I said, this will be a very common mistake. You need to be very careful. Then you will be able to calculate kilojoule per kilogram. So you don't have to convert it again. Okay, because it's a kilojoule per kilogram, kilojoule per kilogram. So that's your final answer, right? So that's for question 2, and for question 3. So question 3, again, mass flow rate. So it's not a fixed mass, expands through a turbine. So immediately you need to understand that we're talking about an open system again. Generator work. Okay, so for any open system, as I said, there's only one equation. Why not just write them down? Write that equation down. Okay, dot so this actually make it easier for you to start with, because sometimes you will find that there's a lot of information in the questions and you don't know where to start. So why not just write the equation down and then to see what we can do with this equation. Okay, so now we can see that because this is quite a complicated equation, we're going to do some simplification as well. So neglecting change in potential energy and kinetic energy. So that's potential energy, kinetic energy. So we're neglecting changes. Now we only have this left. Okay, so we can write and the question asks us to calculate the heat transfer rate. Okay, the rate, because I have a dot there, so we're calculating Q dot, which is equal to W dot. So that's it. We're just going to use that one, which is equal to W dot has been given. Okay, 1165. So it's in kilowatts already. Okay, right units here, so that we can check it later. M dot 2.3. So it's kilogram per second times H2 H1. So H2 H1 both are given. So that's 2336 H2 subtract H1. So that's in kilojoule per kilogram. So we times these two, kilogram per kilogram cancelled. You've got a kilojoule per second, which is actually kilowatt already. So you can see kilowatt. Okay, so the final answer must be kilowatt as well. And then just do these calculations, which will give you the final answer of kilowatt. And here, right? So in the unit of kilowatt, so you don't have to do anything else. So that's your final answer. So now let's have a look at the final one. The final question 4. Again, so this is enters open system. Open system, as I said, we only have the two equations. Okay, so the final equation is how to calculate the mass flow rate. Okay, the mass flow rate can be determined by the area c. Okay, c is a velocity. Okay, and the lowercase v. So this v is not velocity. Be careful about that. In this module, in thermal, okay, in thermal, v stands for specific volume. Actually, I'm written here, just to avoid any confusion. So we're just going to use that. Now I'm going to write this down: m dot times a c over v. Okay, we need to calculate the area at the inlet in the unit. So that's, we're calculating a here. So just to rearrange it, a is equal to, move v over there. So I'm times v and divided by c. Okay, just arrange it. M dot 2.4 v specific volume over c velocity 125. So we can have a look at each unit. Actually, this is kilogram, cubic meter per kilogram, meter per second. You can see everything is perfectly in SI-based unit. This will definitely give you SI-based unit for area as well. Okay, so this must be in unit of a cubic meter, square meter squared for area. Okay, and this, the answer is however, in the question, be careful. So that's, you should give the answer in the unit of a centimeter squared. Okay, so this is because 1 meter is 100 centimeter. Okay, and if you write in order, tend to order, so that 1 meter squared is equal to 10 to the power of 4 centimeter squared. Okay, so that your final answer. You can times that to convert to centimeter squared. Okay, and this will give you a final answer of 3.84. Okay, so 8.4 centimeter squared. So that's your final answer. Okay, so that's the end for quiz 3.